बिस्मिल्लाहिर्रहमानिर्रहीम। हमारी आज की जो डिस्कशन है वो क्वांटम स्टेट्स के बारे में है। तो हमारा जो टॉपिक है डिस्कशन का, डेट इज़ क्वांटम स्टेट्स एंड डीजेनरेसी। तो बेसिकली हम दो चीज़ें जो है वो अंडरस्टैंड करेंगे इसमें। क्वांटम स्टेट किसे कहते हैं और डीजेनरेसी किसे कहते हैं। तो जैसे कि हमने 3 डायमेंशनल पोटेंशियल वेल का केस देखा है, तो उसके लिए जो एनर्जी की वैल्यू आपने कैलकुलेट की है वो वैल्यू थी En is equal to h square over 8m a square n x square plus n y square plus n z square. In this equation, these nx, ny and nz are basically quantum numbers. So there can be several combination of these quantum numbers. Each set of these quantum numbers is called a quantum state. However, among these combinations, several combinations are those for which the energy remains same. Although the set of quantum numbers are different, but the overall energy will always become the same value. To understand it, we can take several examples. So I have a chart over there for the quantum numbers nx, ny and nz. For first example, I take nx is equal to 1, ny is equal to 1, and z is equal to 2. I take another example. For it, I just change the positions of these quantum numbers 1, 2, 1, and for the third example, I again reshuffle these quantum numbers to get 3 different quantum states. So these are the examples of 3 different quantum states. Now if you put all these combinations in this equation, you always get same value of the energy. Although if you found their wave functions, these wave functions must have different values. So if I draw their wave functions like psi 1, 1, 2. So first of all, the coefficient 2 over a 3 by 2 sine. Here you need nx by x over a. So nx is 1. So it will be pi x over a sine pi y over a sine this one 2 pi z over a. For second case, your wave function will be psi 1 to 1. So the constant is same. This will become sine pi x over a sine, okay, due to this will become 2 pi y over a, and due to this will become sine pi z over a. Similarly, you can write it for this. So that will be 2 over a 3 over 2 sine 2 pi x over a sine pi y over a and sine pi z over a. So it is clear from these three equations that these are three different wave functions. But if you use three different wave functions and use this equation to calculate the value of energy, then you get 1 1 2 will be equal to E 1 2 1 will be equal to E 2 1 1 y. Okay, let's check by putting the value of any set of the quantum numbers like the first one, and you always get the value 4 5 6. Okay, 6 h square over 8 m a square. So this is the value of energy for all these three combination. So these three values results in a single value of energy. So you can see quantum states are different like this. Wave functions are different, but the energy is same. So this type of quantum states are called degenerate states. So we have to look at this, that how many states are there which are degenerate. So like in this case we have three states. So this type of degeneracy is called threefold degeneracy. Okay, now we are moving forward. So what about the other states? So all the states which have unique energy are called non-degenerate state. For example, if we take a quantum state having the same quantum numbers like nx is equal to ny is equal to nz is equal to 1 or 2 or 3, in that case there is only one option, there is only one combination of the states like 1 1 1. So this is an example of non-degenerate quantum state. Okay, now the question is, can we break this degeneracy? How to break this degeneracy? So to understand it, we have to make certain change. which can split these energy levels, which are initially consulting, which are initially have same energy. To understand this concept, we take the example of threefold degenerate states like 2 1 1 1 2 1 and 1 1 2. These are the quantum mechanically three different states but energetically same. So to break their degeneracy, we make a small modification. So to achieve this, uh, we suppose only one dimension like x-axis. So we find the energy associated with the first state 2 1 1 along x-axis. So we use our first equation, this one, to find, we use only this part of this equation, this part. So n x square h square over 8m square. Square. So this will be h square over 8m a square into 2 square. So this will be 4 h square over 8m a square. So this is the energy associated with only x direction for the 2 1 1 state, and for 1 2 1 and 1 1 2, the value of x is same, so they should have same value of energy. And using the same relation, this one, you can estimate the energy, which will be h square over 8m a square into 1 square. So the value is h square over 8m a square. So initially, overall, if you consider all dimensions, all three states have same energy, but if you suppose it's any of its individual dimension, like we choose x dimension, so we have this value for the first state along x-axis, and this for the other two along x-axis. Okay, to break the degeneracy, we have quantum well having dimension A like this. Okay, we make a small change by increasing its dimension by A plus dA. Okay, we all know when you increase the width of potential well, the value of energy level relatively reduced by a bit. Here we know that this change is very small, so we can mathematically write it. dA is very, very less than A. Okay, so the initial case is the value of energy for the first state is 4h square over 8ma square. When you introduce dA, then you replace A by A plus dA. Okay, then the value will be 4h square over 8m A plus dA square. So the decrease in energy is, as the denominator increase, so energy value of the energy should be decreased, can be found by taking the difference. A2 is equal to 4 h square over 8 m a square minus 4 h square over 8 m a plus dA square. Okay, take common for h square over 8 m into 1 over a square minus 1 over a plus dA square, or take LCM a plus dA square. So this is a square plus 2a dA plus dA square minus a square. So this is cancelled. Here we want to make certain approximation on both numerator and denominator. Okay, as dA is very small, so dA square approaches to 0, and if you take the denominator, this is a plus dA square can be written as a square into 1 plus dA over a square using binomial expansion. A square into 1 plus nx 2 dA over a. So as a is very greater than dA, then this second term can be ignored. So we simply get a square into 1 a square. Okay, so put these values. Okay, so put these values in this equation. You get 4 h square over 8 m into 2a dA divided by a square into a square. Okay, and this will become 4h square over 8m, and this is cancelled by one of these, like this, so this will become 2dA over a cube. Or simply, if you want to write it like this, h square over 8m a square, so this 4 into 2 becomes 8dA over a. So this is the decrease in the energy of the first state by the introduction of this small change dA. Okay, we apply same phenomena to find the change in the energy. For the second case, for other states, so for other state, your change in the energy will be equal to initial energy is h square over 8m a square minus h square over 8m a plus dA square. So use the approximation that we previously used to solve this. So you simply get the value of energy h square over 8m a square into 2 dA over a. Okay, now we want to check that does the degeneracy breaks or not. To find it, we calculate delta E is equal to E2 minus E1 h square over 8m a square. I take this common, this one, and from the previous equation, this one, So you simply have 8 dA over A minus 2 dA over A. Okay. So this will become h square over 8 m A square to 6 dA over A. Okay. Now we check the degeneracy. Either the degeneracy is break or not. So we focused on a graph that is presented in our book to check it. So I draw the same graph and explain it for you. Okay. So now focus on this graph. We want to check either the degeneracy break or not break. Okay. So these are the three states. 2 1 1, 1 2 1, and 1 1 1. All are degenerate states. Okay. So how much is the change in the energy of the first state by the introduction of an additional width dA? Okay. So what is this one? H square over 8m A square 8 dA over A. Okay. And what is the change in the value of second state? Okay, that is h square over 8m A square 2 dA over A. Okay, so let these two states have a reduced energy, which is like this 1 1 2, and this reduction is, as we calculated, h square over 8m A square 2 dA over A. Okay. Okay, now we talk about this one. So its energy is reduced by a larger amount, and that is like this. That is h square over 8m A square 8 dA over A. Okay, so for a given state, overall that should be h square over 8m A square 8 dA over A. So this remaining part is equal to this difference. And this difference is h square over 8m A square 6 dA over A. Okay, if you look at this graph, it is clear from the graph that initially all the three states have same energy, and after the introduction of this additional change, dA will left these two states with reduced energy, but still they have degeneracy. But this state have a larger reduction in its energy. So these have different energy than these other two states. So therefore, it can be clearly seen from this that degeneracy can be break by changing the dimensions of the quantum well or the potential well. So Degeneracy is very much dependent on the environment of the particle which have the energy in these states. This is all about quantum states and degeneracy. Hopefully, uh, you understand what we discuss here. If you have any question, you can ask. Thank you.